problems, and we're going to do practice problems together to get you ready for exam. The problems I'm about to put on the board here, and we're about to do them, these are really, really good problems to get you ready for exam. So please pay attention and make sure you can do this. Stay with me. All right, here's our first problem. And after I put up each problem, pause me, do the problem, and then unpause me, and then let's go over the answer together. It says, what mass of carbon monoxide is needed to react with O2 to produce 1900 kilojoules of energy? Now, what I've given you here, I give you the delta H of the formation. By the way, how come I did not give you the delta H of formation for O2? Hopefully you're saying it's because O2, delta H of formation, is basically how much energy you need to make something from its elemental form. Energy change to make something from its elemental form. Now O2, that's how it exists in nature. That is the elemental form. I don't need to make it. So O2 has a 0 kilojoules per mole of delta H of the formation. It has no delta H of formation, again, because that's how it exists in nature. I don't need to make it. So far, so good? Okay. Now, what you got the delta H of the formation. Because you got the delta H of the formation, what is the one piece of information you can figure out if I'm giving you the delta H of the formation? You go, okay, every time I have a delta H of formation, what I could figure out the delta H of the reaction. And the delta H of the reaction would be product minus reactant. It would be product minus reactant. You agree with me so far? Okay. So that means I'm going to add up all the product, I'm going to add up all the reactant, and I'm going to subtract them from each other. So carbon dioxide is my product. Here's the delta H of the formation is minus, it's 393 kilojoules per mole. But you have to remember, because it's kilojoules per mole, you have to multiply it by the coefficient by the mole ratio, right? And right here, this is 2 moles of that we have. So then the moles can cancel out. That's the only product I have. So this is my product minus my reactant is carbon monoxide is 110 kilojoules per mole. Okay, I multiply by 2 mole, right? Because I have to multiply it to get rid of the mole. All right, and that is, and oxygen is just 0, so plus 0 for oxygen. I add up all the product, I add up all the reactant, I subtract them from each other. If I do that, what I end up having is negative 566 kilojoules of energy. Again, I want to try to go slow, go over every single detail to make sure you get this down. The moles cancel out. So what I end up getting is just the kilojoules, because the moles cancel out. That's key. Now, what does negative mean? That means this is an exothermic reaction. This is a favored reaction because my net profit, I'm actually releasing energy to the to my environment, to my surrounding, because we say that delta H basically is a net profit that you end up getting, and it's an exothermic reaction, so I ended up releasing energy to the surrounding. So far so good. So let's take a step back. Again, I give you the delta H of the formation. So basically that's the energy change when you make something from its elemental form. And because O2, that's the elemental form, is going to be 0. Every time you had the delta H of the formation, you can figure out the delta H of the reaction. Product minus reactant. Don't forget to multiply by the moles, so the moles can cancel out. I end up with kilojoules. That part is pretty easy. You got this down. Now the next part is, what mass of carbon monoxide is needed to react with O2 to produce this much energy? Now there's 2 ways to do this. The way that I like to do it is a low-key way, and setting up a proportion. I love proportion. So pay attention to this part. Right here, this reaction releases 566 kilojoules of energy. Do you agree? Okay. So this reaction right here, it releases 566 kilojoules of energy. Do you agree with that? Okay. Now, for this reaction to release 566 kilojoules of energy, how many moles of carbon monoxide is needed? 2. Okay. So if I have 2 moles of carbon monoxide react with oxygen, 566 kilojoules of energy is released. Yes, if I have 2 moles of carbon monoxide react with oxygen, 566 kilojoules of energy is released. Now it says, what if we want 1900 kilojoules of energy to produce, right? And I'm going to erase this sign because again, this sign doesn't mean anything. It just means release, right? I already know it's release. What if you want to produce or release 1900 kilojoules of energy? Again, I just erased the sign because the sign just means exothermic, endothermic. It doesn't mean much else. I already know this is exothermic. Produce also means exothermic. Okay. Now, I want this much energy. You can do a proportion. So, how many moles of carbon monoxide I need? I'm going to repeat this again. So, this reaction over here, this reaction over here, when you run this reaction as is, which is 2 moles of carbon monoxide with 1 mole of oxygen, producing 2 moles of carbon dioxide, 566 kilojoules of energy is released, as is this reaction. Now I'm asking you what I want. I want 1900 kilojoules of energy. So if I want 1900 kilojoules of energy, how many moles of carbon monoxide do I need? Okay, so if I solve for x, what x is going to be 6.7 moles of carbon monoxide. Now, it asks you for mass and not for moles. That's okay. If I have moles, can I convert it to mass? Yeah. Using molecular weight. 1 mole of carbon monoxide is 28 grams. So what that means is the moles will cancel out. What I end up getting is 190 grams of carbon monoxide. So what does that mean? I need 190 grams of carbon monoxide to produce 1900 kilojoules of energy. Hopefully you guys follow that. Yeah? I'm going to go over it one more time. So this reaction as is give 566 kilojoules of energy for 2 moles of carbon monoxide. I get 2 moles of carbon monoxide, this much energy I get out. But I want this much energy. I want this much energy. So how many moles of carbon monoxide do I need? Times molecular weight. This many. So if you get 190 grams of carbon monoxide reacted with oxygen, you would end up getting this much energy out of it. Now, the proportion is how I like to do it because it's kind of low key, but you don't have to do it that way. So the other way to do it, and some people might like that because it's canceling out, basically they give you 1900 kilojoules of energy and you're going to cancel it out for 2 moles of carbon monoxide in a reaction. You got 566 kilojoules of energy. So then the kilojoules cancel out. Now you have moles. And then you convert moles to gram. 1 mole of carbon monoxide is 28 grams. So then the moles get canceled out. And then what you end up getting, the same number, 190 grams of carbon monoxide. Okay? Again, one more time. 2 moles of carbon monoxide gives me 566 kilojoules of energy. How many moles do I need to make 1900 kilojoules of energy? It could be just a proportion. Okay, beautiful. Ready for next one? Here is my next problem. Pause me and then do this problem and I'm going to go over it with you. So every time you have questions like this, the best thing to do is to draw it out. And I'm giving you really hard problems here, but hard problems are good. I'm going to give you hard problems to get you ready for the exam. I have a glass of water. I have a glass of H2O, okay? And the temperature of this is 65 degrees Celsius. That's pretty hot, right? My water is hot. Now, in normal life, when your water is hot, what do you do? When your water is hot, what do? you add ice to it, right? If I have a warm water, but I don't want to drink warm water, I add ice to my water, so my water will cool down, right? So that's what you do on a daily basis. You just don't go and say, exactly how many grams of ice do I need to add to my warm water to cool it down. You just keep adding ice until it's cool. But chemists, we take it to the next level. We want to know exactly how much ice do I need to cool my water from 65 degrees to 0 degrees Celsius so I can have nice cold water to drink. Okay, does the question make sense? So I have a water here. My water is warm, 65 degrees. I don't want that. What I'm going to do, I want to take all these ice cubes and I'm going to add these ice cubes to my water. If I add ice to my water, what happens is it's going to cool it down. But I want to add enough ice to cool it down to 0 degrees Celsius. I want to add enough ice to cool it down to 0 degrees Celsius. That's my question. So far, so good. Okay. Now, what is going on here? What is going on here? When you add ice to water, when you add ice to this water liquid, there are a few things that is going to happen. One thing that is going to happen is we're going to have a T change, right? Because if you add ice to water, the temperature of your water is going to change. That's my T change. Now, you've done this many times. If not, go do it right now. Take a warm water, add ice to it. Will the ice melt? Yeah, the ice is going to melt. So I'm also going to have a P change. Why? Because the ice is going to melt. I'm going to have a P change because the ice is going to melt. It's going to go from solid to liquid. It's going to go from solid to liquid. The ice is going to melt. Okay. Now, when the ice melts, is that an endothermic reaction or is that an exothermic reaction? If you remember, I asked you last time that every time you're doing a phase problem, write this down. Solid, liquid, gas. When you come down, that's an endothermic reaction. And then when you go up, that's an exothermic reaction. Okay? Let's go over this one more time because I need you to really understand it. So every time you have a phase change, what I want you to do, I want you to write down this solid, liquid, gas. When you come down, that's an endothermic reaction. You need energy for this phase change. When you go up, is an exothermic reaction. You release energy. And you already kind of know that. We talked about it last time. Because when liquid goes to gas, if you have a kettle of water and you want to bring it to boil and go to the gas phase, you would have to heat it up, right? You heat up water to go from liquid to gas. So it's an endothermic process. And the other way, it's going to be an exothermic process. Okay, so here, what's going to happen again? I'm going to add ice to water. I'm going to add ice to water. If I add ice to water, I know the temperature is going to change, right? Because you do it right now. If you have a warm water, you add ice, your water is going to cool down, right? So it's not going to be warm anymore. Also, your ice is going to melt. So there is a P change, a phase change also. When you go from solid to liquid, what is that? That is an endothermic process, right? This is an endothermic process. That's my endothermic process, okay? Now, when you have an endothermic process, again, solid going to liquid, what just happened? Solid going to liquid is an endothermic process. Now, what does an endothermic process mean? What does this mean? It means it needs energy. Endothermic process means needs energy. So in order for ice to melt is endothermic process, it needs energy. Now here's what's key. Where is ice going to get the energy from? It is going to get it from water. It's going to get it from water. Again, so ice is going to melt. That's an endothermic reaction. For solid to go to liquid, it needs energy for this to happen. It needs energy to happen. Where is it going to get that energy from? It's going to get that energy from the water. So ice is going to get the energy from the water so it would melt. The ice is going to get the energy from the water so it would melt. You guys are following me so far? Okay, so ice gets the energy from the water, so it would melt. Beautiful. Now, we said that we are going to have a T change. So if I have a T change, I know the formula for my T change is mass times specific heat times T final minus T initial. Okay? Now, water did a T change. So my energy is going to equal, what was the mass of water I used? In your glass, there was 50 grams of water. Is water liquid? What's the specific heat? 4.184 joules over gram degree Celsius. What do you want the final temperature to be? Remember, what you want the final temperature to be is 0. You want to go from 65 to 0. So my final temperature is 0 degrees and 65 degrees is my initial temperature. So far so good. So when I do this, I get 13,600 joules of energy is what I get. Okay. Now, what does this mean? This is an exothermic reaction, right? Now, what does an exothermic reaction mean? That means water lost energy, because you release energy when you're in exothermic reaction. Water lost energy. Water released energy. Now, if water lost energy, who is going to get that energy? Ice. Ice will get that energy. That's really key in this chapter. If you can understand that, you can do any problem. That one loses, the other one gains. Water lost the energy, is an exothermic reaction, is going to release the energy. Who gets that energy? Ice will get that energy. Ice will get that energy. Now, when ice will get that energy, then what is it going to do? It's going to melt. Ice is going to get that energy and then is going to melt. So next thing we're going to have a phase change. The phase change is going to be mass times delta H of fusion. Why is delta H of fusion? Because what is fusion again? Fusion is melting. When solid goes to liquid, that's fusion. That's melting. Okay? Now, I told you guys, every time you have phase change, I want you to write down solid, liquid, gas. You go up, down is positive. You go up is negative. So what we're doing, we're going from solid to liquid is an endothermic reaction. Okay. Now here, what is the mass of ice? That's what we're trying to figure out. How much ice do I need to add to my water to go from 65 to 0? The delta H of fusion is 333 joules per gram. Okay. I cannot have two variables. I must have the energy also. Do I have the energy? I do. You know what we talked about? We said water is going to lose the energy. Ice will get that energy. There's a conservation of energy. One loses, the other one gains. So if water loses 13,600 joules of energy, how much will the ice get? 13,600 joules of energy. But remember, losing energy, the sign is negative. What is going to be the sign right now? The sign is going to be positive because it's going to receive it. It's going to get it. When you get the energy, the sign is positive. So if we solve for x, what we get is 40.8 grams of ice. Alright, now the key to this problem, which was a hard problem, is to understanding kind of the concept. You have a warm water. What do? You add ice. And you add ice until it cools down. Chemist takes it to the next level. We say my water is 65 degrees. I want to go to exactly 0 degrees. How much ice do I need to add? Normal person would just keep adding ice until it's cold. No, chemists want to know exactly how much ice we need to add to make this happen. So we know to make this happen, to make the T change, this much energy will be lost by water. Who gets the energy? Ice will get that energy and is going to melt. So that's how much ice I need. All right, nice job. Ready for the next one? Let's keep going. Rank the following from the lowest to the highest vapor pressure. Here is my hint to you before you pause me so you can do this. Here's my hint to you. Figure out IMF first. Figure out the IMF first. And sometimes to figure out the IMF, you need Lewis structure. You need the Lewis structure in order to figure out the IMF. Okay? All right, pause me and then do this. All right, I have H2S. If I draw, let me draw it in a different color so you guys don't get it confused. Let's go black. Okay, so H2S. The S is going to be in the middle. And I have hydrogen and hydrogen. This is also a good practice problem for Lewis structure. Now, if you look at this, this is polar. Do you guys agree? This is polar. So I go H2S. H2S is not ionic. H2S does not have hydrogen bonding because hydrogen bonding you have to have NH, OH, or FH. Now, H2S is covalent. Now, if you're covalent, you have to say you're polar or non-polar. Is covalent and is polar. If it's covalent and is polar, what do you have? You have dipole, dipole. You have dipole, dipole. Okay? You have dipole, dipole. Now, I mentioned to you guys before that count hydrogen as a non-metal. Count hydrogen as a non-metal. Okay? Count hydrogen as a non-metal. Now, also we said if everything has London dispersion, because London dispersion is temporary dipole, and everything could have temporary dipole. Now here we have HF. Is it ionic? No. Again, count hydrogen as a non-metal. Is it hydrogen bonding? Yeah, because it has HF. It has H bonding. Anything that has HN, HO, and HF directly attached is going to have hydrogen bonding. Perfect. Now, this one is also covalent. Now, is it polar or non-polar? It's polar. So, if you're polar and you're covalent, what else do you also have? You also have dipole, dipole. And we said you have London dispersion too because anything could have temporary dipole. Okay. Now, F2. I want to draw F2 out. Is it ionic? No. Hydrogen bonding? There's no H. Is it polar or non-polar? Is non-metal, two non-metal together, and is non-polar. So if you're non-polar, the only thing you have is London dispersion. The last one is H2. Is it ionic? No. Hydrogen bonding? No, you don't have HN, HO, or HF to have hydrogen bonding. Is it polar or non-polar? This is also non-polar. Again, count hydrogen as covalent to help out. It is non-polar. So what's going to happen is going to have London dispersion. Is going to have London dispersion. All right. Now, which one would be my highest intermolecular forces? My highest intermolecular forces is going to be this one right here. This is my highest IMF because it has hydrogen bonding. What's going to be after that? Then it's going to be this one. It has dipole, dipole. Now, between these two, which one is going to be higher? Remember, the one that has a higher molecular weight is going to have a higher London dispersion. The one that has a higher total number of electrons, not valence. Okay? So, higher molecular weight or higher total number of electrons, not just valence, it would have a higher London dispersion. Why is that? Because you have a higher chance of temporarily creating a dipole. So between these two, this is going to be had and this is going to be my last one. Now, if you remember, we said this is the opposite. The higher intermolecular forces would be the lower vapor pressure. Because remember that? We said when the IMF goes up, everything goes up except vapor pressure comes down. Why? Here's why. Vapor pressure is a tendency for liquid to go to gas. If you have a high intermolecular forces, the liquid does not want to go to gas because they're holding on very tightly to each other. So IMF goes up, lower vapor pressure. So if I want to rank these guys, how would I rank him? The higher IMF, it would have the lower vapor pressure. So for vapor pressure, I would get H2. I'm sorry, it was, give me 1 second. Yeah, H2 would be the highest one. I asked you to lower, so let me actually do what I had asked you to do. Give me 1 second. There we go. So the lowest one would be HF, and then after that is H2S, so the opposite. F2, and then H2 is the last one. So far so good? Okay, beautiful. Ready for next one? We're just gonna keep going. You have two balloons in the same room. One is filled with N2, the other one with carbon dioxide. Both have the same mass of gas. Now answer these questions. So hopefully you pause me and you do this. Now here's the key when you look at this. They're in the same room. If you're in the same room, you have same volume and you have same temperature. You have same volume and you have the same temperature, okay? You have the same room, means you have the same volume and you have the same temperature. Now the other key is they have the same mass. But here's what I want you to really understand. Same mass does not mean they have the same number of moles. And mass doesn't really matter. What really matters is moles. What really matters is moles. Now, when you have the lower the molecular weight, that means you're going to have higher number of moles. That means you're going to have a higher number of moles. Okay. So it says, which balloon has a greater pressure? Let's do this together. Greater pressure. So I'm talking about gases. PV and RT is what I know. I want to write down PV and RT. I'm in the same room. If I'm in the same room, I have the same volume. That's going to go away. And I have the same temperature. That's going to go away. Okay? I'm in the same room, same volume, and I have the same temperature. And the R will also go away. Now, which one is going to have a greater pressure? Now, the greater pressure would mean it would also have the higher number of moles. Why is that? Because they're on the opposite side. If this goes up, this one has to go up, so they would equal to each other. They're on the opposite side. If they're the same side, one goes up, one goes down. But opposite side, if this goes up, this also has to go up. Okay? So which one is going to have a greater pressure? The one that has more moles. More moles does not mean more mass, right? They have the same mass, but it does not mean they have the same moles. The one that has a lower molecular weight is going to have more moles. And I did this in a lecture before. You can also make up numbers to yourself. They have the same mass. Let's say they both have 10 grams of N2 and CO2 converted to moles. See which one would have the higher number of the moles. And in this case, it would be N2. It would be N2 because N2 is going to have the higher number of the moles because it has a lower molecular weight and a higher pressure. Again, if you're not understanding this part, if you're having a hard time to grasp it, sometimes I do too, just say same mass. You have 20 grams of each divided by the molecular weights and then see which one is going to give you more moles. And you'll see that would be N2. Which balloon has a higher velocity? Okay, which balloon has a higher velocity? If you remember, velocity is how fast you can go around. Now, how fast you can go around, it depends on how light you are. The lighter the atom, they can move around faster. Same as us, right? The lighter we are, we can move around faster. So you have to go with the lighter guy, with the one with the lower molecular weight, which would be N2. Okay. Which one has a greater average kinetic energy? If you remember, for average kinetic energy, we said average kinetic energy, it only depends on temperature. Now, do we have the same temperature here? Same room is the same temperature. So it would be the same. They both will have the same average kinetic energy because kinetic energy is only dependent on temperature. Which balloon was effused faster? It's the same thing. Diffusion, velocity. The lighter guy can run around faster. You run around faster, you find a hole faster to get out, right? So the lighter atom will have a faster effusion. Lighter walk around faster and it can find a hole. So far so good. Okay. Are you ready for next one? Let's do this. Here's our next question. Okay. So I ask you how much energy is released and absorbed when 56 grams of water is produced. Now, this is kind of the same. We've done something very similar to this today. So I'm hoping if you pause me, you're going to be able to do this problem easily. Here in this problem, I give you the delta H of the reaction, right? If I give you the delta H of the reaction, what is the one piece of information you can easily figure out? The delta H of the reaction. So if I give you the delta H of the formation, you can easily figure out the delta H of the reaction. Okay? Now, let's go over this again. I give you all the delta H of the formation, that's energy change you need to make something from its elemental form. But I did not give you the delta H of the formation for sulfur. Why is that? That's because that's how sulfur exists in nature, right? So it would be 0. That's how it would exist in nature. Okay, we have the delta H of the formation. Product minus reactant would give a delta H of the reaction. Let's do that. So sulfur is 0. Water is negative 286 kilojoules per mole. We talked about it. We have to multiply it by mole. I have 2 moles of water, coefficients are the mole ratio, so the mole can cancel out. Alright, so now this is going to be my product minus my reactant. My reactant is H2S, so negative 21 kilojoules per mole. How many do I have? I have 2 moles, so the moles can cancel out. And SO2 is minus 297 is just 1 mole, right? So I just times it by 1 mole. So again, the moles can cancel out. You times it by the coefficient. Don't forget that. You times it by the coefficient. So product minus reactant. What I end up getting, if I do product minus reactant, I get negative 233 kilojoules of energy. Negative 233 kilojoules of energy. So what that means is this reaction, the way it is going to produce, is going to release energy, 233 kilojoules of energy. So far so good? Okay, that part you know how to do. Now, think about it this way. They ask you when 56 grams of water. First of all, every time they give me gram is not going to do me any good. What should I convert it to? You should convert it to moles. Let's do that. 56 grams of water. Grams in chemistry, we don't like, we love moles. That's what we know. 1 mole of H2O is 18 grams. So the grams will cancel out. What I end up is 3.1 moles of H2O. Now we did this at the beginning of the lecture. Remember we talked about the way I like to do it is proportion, right? So this reaction, the way it is, it will produce 233 kilojoules of energy. When you produce 233 kilojoules of energy, how many moles of water do you need? 2. So if I have 2 moles of water, I am producing 233 kilojoules of energy. Okay? If I have 2, don't do that. If I have 2 moles of water, I'm producing 233 kilojoules of energy. Okay, now how many moles of water do I have? I have 3.1 moles of water. How much energy am I producing? So far so good? Okay, so again, this reaction as is, 233 kilojoules of energy is produced, right? I can even put it at minus because it's produced. Again, the sign doesn't mean anything. It just means exo endothermic. You know already in your head. So 2 moles, 233 kilojoules of energy is released. Now, if I have 3.1 mole, how much energy will be produced? And the answer is negative 360 kilojoules of energy. Okay, one more time, and then I'm repeating myself. This reaction, as is, it would produce 233 kilos of energy. Now, I need 2 moles of H2S and 1 moles of SO2 to produce 3 moles of S and 2 moles of H2O. So, when I produce 2 moles of H2O, 233 kilojoules of energy is released. Now, if I have 3.1 moles of H2 that I want to produce, how much energy is it going to be released? Okay, you can do it as a proportion. Nice job. Okay, next one. What I'm asking you to do, I want to ask you to rank the following from the lowest to the highest boiling point. CH4, CCl4, SeO2, and then calcium chloride. Now, I gave you a hint before, right? So to figure out the physical properties, you figure out the IMF first, right? And then you go from there. That's my hint. We did this. Again, I'm giving you some exact type of problem. I'll be repeating some of the questions to make sure that you guys feel very comfortable. Pause me, do this. CH4 is not ionic. I'm going to draw it out. If I draw it out, I can see there is no hydrogen bonding because it has to be NH, OH, FH directly attached. And is it polar or non-polar? It's non-polar. You have to go back. It's covalent, non-polar. So the only option I have is London dispersion. CCl4. I want to draw it out. Again, it's not ionic. It doesn't have any hydrogen, no hydrogen bonding. When I draw it out, it's also non-polar. It's covalent, 2 nonmetals together, is non-polar also. So what it also has LD. Go back to your notes to figure out the non-polar and polar geometry. SeO2. I'm going to draw it out, 2 nonmetals together again. If you draw it out, I'm not going to go over the Lewis structure, but if you need to review those. Now, this is polar. It has a lone pair on top. It's polar. We have more electrons located on this side than the other side. So it's polar. Okay, it's not ionic. There's no hydrogen. There's no hydrogen bonding. It's polar. It's 2 nonmetals together. So it's covalent, but it's polar. If you're polar, what you have deep, but you also always have London dispersion. Now, calcium chloride, that's a metal and a non-metal together, right? That makes it easy. Every time you have a metal and a non-metal together, you don't have to even go farther than that. You go, oh, that's ionic. And I mentioned before, count hydrogen as non-metal when you're doing that. So that's ionic. What is my highest IMF? My highest IMF would be ionic, then dipole. Now between these two, we talked about that. The one that has a higher molecular weight, higher total number of electrons is going to have a higher London dispersion, which would be CCl4, because then you have a higher chance of temporary having a temporary dipole. Now, here's my IMF. If the IMF goes up, I would have a higher boiling point. Here's why. The higher intermolecular forces, that means you're holding on together really tightly. If you're holding on together really tightly, it's going to be harder to heat it up, so it's going to have a higher boiling point to break those intermolecular forces, so it's going to go to the gas phase. So higher intermolecular forces, you have all these, that means you're holding on very tightly together, so it's going to be harder to break the intermolecular forces, so it's going to have a higher boiling point. You have to put more energy to break the intermolecular forces, so it will have a higher boiling point. Hopefully that makes sense. Okay, so higher IMF would end up being higher boiling point. So from lowest to highest, CH4, CCl4, SeO2, and CaCl2. All right, nice job. Hopefully you guys are getting this down. Here's our next practice problem. We're almost there. 2 more, promise you. Now, when you do this one, we're talking about density, we're talking about height, we're talking about mercury. What are we talking about? We're talking about a barometer, right? One of the equations that we did at the very beginning of the exam 3 lectures was density of mercury times height of the mercury equals the density of the liquid times the height of the liquid. Okay? Now, let's plug it in. Density of liquid is 13.6. Yes? Now, in this question, they ask you for height of the liquid. I know this is my x. Okay? Now, they also tell me the pressure of the liquid. They tell me the pressure of the liquid. Okay? And let's see. Let's go over this one more time. So mercury is 4 times denser than liquid X. So I have a density of mercury, but it says that the density of the liquid is 4 times denser. So mercury is 4 times denser than a liquid of X. Okay? What height of liquid X in millimeters is equivalent to pressure of 20 centimeter mercury? Let's go back again over this because I just confused myself. I'm actually going to erase this since I confused myself, which means I just confused you. In this problem, what they ask you for, what is the height of liquid X? So I'm going to say this is my X. That's important, which means every other variable should be given because I cannot have more than one variable. Every other variable should be given. Okay? Density of mercury, that's a constant, is given to you, 13.6. Now, they don't give you the density of the liquid, but it says that mercury is 4 times denser than liquid X. So if this is 13.6, which means this is 13.6 divided by 4 because mercury is 4 times denser. Okay. They also give you the height of the mercury. It says the height of the mercury is 20 centimeter of mercury, the height of the mercury. Everything has to be in millimeters, so I'm going to convert this to millimeters. It will be 200 millimeters. 200 millimeters of mercury. Everything has to be millimeters, don't forget. So now I have everything, and my X is going to be 800 nanometer. The thing to kind of look out for when you have this kind of problem with a barometer and then the density of the mercury and then the pressure, which you might have in your lab exam or lab quiz too. When you put this reaction equation down, you can only have one variable, figure out what they're asking you for, plug in the rest of them, and don't forget everything has to be millimeters because everything is going to be millimeters of mercury. It has to be millimeters. Yeah, nice job. Ready for last one? Okay, last one. Nice job hanging in there. What is the density of chlorine gas at STP? What is STP? Standard temperature and pressure. For gases, standard temperature and pressure is 1 atm and 0 degrees Celsius, which is 273 Kelvin. This is the STP for gases. STP for thermodynamic, for reaction, was different because we do reaction at 25 degrees at room temperature. But the STP for gases is 0 degrees. Okay. What is the density of gases? Now here is the formula for density of gases. Density of gases is equal pressure times molecular weight over RT. That's the formula for density of gases. It's a good formula to know. You can drive it from PV and RT, but it's easier if you just know this formula. Density of gases is pressure times molecular weight over RT. Okay. All right. What is my pressure here? Is 1 atm because it's STP. What is the molecular weight of chlorine gas? This is where people might make a mistake. Chlorine gas, when I say chlorine gas, I really mean Cl2 gas, right? So chlorine gas is not Cl, it's like hydrogen gas, it's H2, oxygen gas is O2, those are diatomic molecule. So the molecular weight of chlorine gas would be 35.5 times 2 because chlorine gas is Cl2. What is R? 0.08206. And what is my T? 273 Kelvin. When I do everything else, you end up getting 3.2 grams per liter. That would be the density of chlorine gas. So make a note of this equation. This equation is for density of gases. And every time you have a density of gases, and density is basically mass over volume. So this is, if you rearrange the PV and RT, you would get this equation.